Okay, thanks very much. And also thank you to Libor and Jairo for the invitation to speak here. It's not a very understandable invitation because I have a dirty secret. I know nothing about magnetism, right? Collinear, non-collinear, alter, all of it. I don't know a damn thing about any of it. And in fact, I was recalling that when I was appointed to my chair in St. Andrews over 20 years ago, they attempted to call me the professor of magnetism. And I refused. I said, that's so unrealistic. I want to be professor of condensed matter physics. And this had ramifications because some poor dean had to inaugurate me in Latin. And he struggled like hell with condensed matter physics in Latin, right? And one of the ways, I have a very fortunate job because we don't really need to be strategic, and somebody decided to give us money and freedom about 10 years ago. I've been in Germany just over 10 years now. And as usual, the truth about the development of this instrument is entirely serendipitous. The way it actually came about was that for the second time during her 5 years in the group, Veronika Sunko, who's definitely the best person who's ever worked with me, she asked, okay, I'm going to stay on an extra year. Can I do something completely different? So that would then be the third completely different thing that she'd done during this 5-year period. And I knew that she was interested at that point in applying to go to Berkeley to work with a longtime friend of mine, Joe Arnstein. So Joe and I said to her, well, how about you get an empty lab and a budget, and you try and build something which will be complementary to what's going on at Berkeley so that the two groups can instigate some level of collaboration that they've never had in the past. And this is the story of what she then did. So now, the other great thing about my job nowadays is that I don't have to try and pretend I'm strategic. I don't have to write grants. I don't have to do all these things. But occasionally, I get linked up with people who do, and I'm a co-PI on a grant called Elasto-QMAT that Jairo co-leads. So for the purposes of that, I thought I had to show the youth that I still, could do some of the dark arts of grant applications. So we've decided to call it the elastoscope. And if any of you are reviewing this grant, it's going to look really strategic, but that's not actually true at all. Right? So I'm going to, but you mustn't say that. So what I'll do today then is I want to tell you about what the elastoscope actually is. Then I'll make some remarks on some stuff which I'm much more familiar with, but it has some relevance to this story, which is a recent technique called the AC elastocaloric effect, which is an incredible technique for measuring thermodynamic quantities extremely precisely. And then I'll give you a couple of examples of what we've done so far with the grandly named elastoscope. But that I'll try and get across the idea that that's only scratching the surface of what it could do. And then I'll give you a summary and some sort of discussion of future prospects and ways in which it might be fruitful to do some appropriate collaborations. So what is the elastoscope? Well, when I think of a microscope, I probably tend to think of this. But of course, you could also think of this. And so you've got to be careful whenever you see the words microscope. And our microscope that Veronika built looks basically like this. It's kind of at intermediate length scales. So the idea is that you have a laser table where you make the choice of optical setups that you're going to put onto the laser table. You have a Montana Instruments optical cryostat. It has a base temperature of 5 Kelvin, but probably not under the conditions that we'll use it under. And that Montana cryostat now comes automatically with a piezo-controlled XYZ stage. So the philosophy of the microscope is fixed optics moving sample. So the resolution is to do with the fundamental resolution of light plus your ability to move the sample around. And the great thing is that that then gives you the ability to set up optics experiments of quite some complexity while still retaining your microscopic capabilities. Nothing I've said there has anything to do with elastic properties. That comes in the final thing that Veronica designed in. We knew we would be interested in applying uniaxial pressure and controllably applying strain to the samples that we were going to do this microscopy on. So she worked with Montana to have a slightly customized cryostat designed that can fit a uniaxial pressure cell. So in the end, we have the ability to have whatever laser-based experiment we want coming in through this window, impinges on the sample, and we can have that sample in a uniaxial pressure rig and use the uniaxial pressure, for instance, to play with domains if they couple to the pressure. So the grand goal then is to have this capability of imaging domains and slow domain dynamics, which we could then help control with the uniaxial pressure. And we could have a range of tools. And as I said before, if there are domains and they couple to strain, we can manipulate them and try and learn something about that from that process. And the kind of the experiments that she designed in, so we have all of the equipment to do that at the moment, would be spatially resolved birefringence, spatially resolved Kerr rotation, spatially resolved thermal diffusivity, all spatially resolved, so I won't keep repeating myself, second harmonic generation to look for inversion breaking. And there's no reason, we're doing everything in effectively a DC mode at the moment, but one of the lasers is an ultrafast laser, so ultrafast pump probe isn't completely impossible either. And when we have the uniaxial pressure cell in the apparatus, I bet you we can do better than this, but at the moment we can only get the experiments down to about 15 Kelvin the way we're doing them now. So these are, in blue, these are what we've done already. And then the even grander goal that we have is to do everything there while still studying the thermodynamics of the compound, of the material. And to do that later thing, I'll tell you about the AC elastocaloric effect, which was, to my knowledge, invented by Matthias Ikeda in Ian Fisher's group at Stanford a few years ago, and is really a fantastic technique. So that says that you have some experiment that you were wanting to do anyway, and you have your sample mounted in one of the uniaxial pressure cells that were developed in our group that you can now buy commercially. And what that pressure cell is that you take your sample and you epoxy it across the jaws of a vise. You then drive that vise externally by applying voltages to these three piezo stacks. And the whole design is such that, say, if you put a positive voltage to the red stacks, you will tension the sample. If you put a positive voltage to the blue stack, you'll compress the sample. And there's some degree of cancellation, not perfect, but there's some degree of cancellation of differential thermal effects as you cool down. Okay, so you were going to do that anyway. And what Matthias pointed out was that in the field of materials, shape memory alloys and things with huge elastic responses, quite a lot of use is made of the elastocaloric effect, which is a very close analogy with the magnetocaloric effect. And it says that if you have a strain-dependent entropy, you will end up getting, and you measure the change of temperature with strain in an experiment, then what you are really measuring, if you like, it's depending on the tensor quantity of the delta epsilon, you're measuring something which relates to or some component of the Gruneisen parameter, right? And so and the point is that this has been used many times with these things with huge elastic responses. But if you want to work with something with a standard elastic response, the kind of thing that we're interested in, you don't have anywhere near the sensitivity that you would need to get a sensible signal. What Matthias pointed out was that we don't need to restrict ourselves to applying big DC voltages to crunch this sample. What we can also do is apply an AC ripple to it. And in fact, it's so sensitive that you can apply an AC ripple in the frequency range, say, 1 kilohertz to 10 kilohertz. And that AC ripple is a change in length of the sample of order parts per million. So it's a very small perturbation to the sample. And you then lock into the temperature response to that AC change. And you get temperature changes of order of millikelvin, which you can actually measure very accurately if you're being careful. Right? And so the genius of Matthias was to realize that this was a new way of doing an AC effect. And in the original RevSci-Inst, they did this. I only reminded myself of this graph recently, but it really, I think, tells you much of what you need to know. So this is one of their favorite arsenides. It has a nematic transition here and an antiferromagnetic transition here at about 100 Kelvin. And you always have the problem with heat capacity there that you have a huge background on your heat capacity from the phonons. So when you attempt to measure the heat capacity signature of these phase changes, in this case, the way they did it was to take a reference sample that didn't have these transitions and do a subtraction. So if you want to do all of this with the heat capacity in a PPMS, you do that subtraction, and that's the kind of level of data you get out. You simply go in and make one measurement of the elastocaloric effect. That's what you get in the red line. And the signal to noise is, just indescribably better, right? And so that's what they were making the point. So here, they haven't even applied, they're trying to do this at zero strain. So they're essentially measuring the critical properties of the material at zero strain in a far better way than was possible before, right? But you can also then add this AC ripple to a big DC strain so you can trace out the phase diagrams of anything with a strain-dependent response. We were very interested straight away in doing that on our favorite superconductor. That's, I'm not going to talk about that in any detail today. It's not that relevant for this workshop. But what is relevant is here, for instance, is the total thermal signal that we're measuring at 8 Kelvin. It's about the AC part of it is an AC temperature change across the whole scale of about 1.5 milli-K. But it's possible to work with thermal precisions if you're careful of microkelvin per root hertz. And that's what that number translating into that data is what you're seeing there. There's essentially no noise visible on the data. And what we're seeing at 8 Kelvin, this is a strain sweep at 8 Kelvin going along here. That signal there, it turns out, is the elastocaloric signal of crossing a Lifshitz transition. And then when you go down to 6 Kelvin, you're seeing that extra dip feature there, which is coming out as this dark blue line. And it turns out that that coincides with a previously unknown magnetic transition at high strain in strontium ruthenate. So I don't really want to over-pitch this. All I want to say is that really rapid phase diagram scanning of interesting materials, if they have a strain response, is perfectly possible using the elastocaloric effect. I always joke with the poor guy who did it that it took him about 2 weeks to get this data set, and it took us about 2 years to write the paper because I insisted, this is raw data, and I insisted that the elastocaloric, the Gruneisen parameter, had to be presented in correct absolute units. And that calibration was what took all the time. And that probably has to be done on a case-by-case basis. And so these aren't necessarily super quick experiments if you want absolute units, but of course you don't always want absolute units.
You never
Run? I never want absolute units. You always want absolute units if you... Yeah, you guys, that's true. You guys just set everything equal 1. Well, that says it all, really. Okay. So the grand elastoscope vision, then, is to have the sample in the pressure cell, to expose the top side of it to the laser light and do everything we can with the spatially resolved responses we might want to see, but also have a thermometer on the bottom side so that either simultaneously or at least in different runs on the same sample in the same conditions, we could get the thermodynamic data out. And by the way, it's not just thermodynamic because, of course, the AC elastocaloric has a real and imaginary part of its response. So the imaginary part is going to tell you about dissipative processes in your material. And so the idea of looking for domain motion in a dissipative part of the elastocaloric signal is something we're very interested in for the future. Okay, so that's the grand vision. What kind of experiments can we actually do with our laser stuff? Well, it turns out that we were really interested in measuring the thermal diffusivity. I don't know if that will ever be useful in the magnetic field, but it was interesting for us. And the way we did that was, and this is all now done in 0 pressure. We hadn't yet got the strain cell in. So what you do there is you send in a pump probe, laser-based pump, which, like in Sebastian's talk, is only there to heat the sample. But you put it through a chopper, so it's an AC pump. And then you put your probe beam some known distance away, and you study the phase with which the oscillatory signal reaches your probe relative to the phase you put in, because that phase is related to the diffusivity using that equation there, and it's frequency dependent, and you have to do all those checks. And the thing that was really interesting to us was that we were actually very interested in the high temperature thermal conductivity of these samples. And thermal conductivity is very dangerous to measure at high temperatures using standard thermal conductivity rigs, because you run very rapidly into radiative loss problems due to Stefan-Boltzmann law. Here, this is very well suited to doing high temperatures better than low temperatures, so the two methods are complementary. And the other thing to say is that while I've put a distance here, you can actually just overlap the pulse and pump probe to get certain kinds of information out with much higher spatial resolution, just because the profiles of the beam are different, and you can model that. So this is the kind of thing we could do on the material we're interested in there. This is the high temperature thermal conductivity deduced from measuring the diffusivity in the laser-based setup and the heat capacity separately. And this is traditional thermal conductivity measurement over the temperature range where it's reliable. And we had to apply a fudge factor because of, we don't absolutely have the calibration of our diffusivity rig sorted out. But the fudge factor is of order 30%. But the point is it's a single factor. And so once we have normalized the data at one point, the good thing is that you maybe can't see it, but the traditional thermal conductivity and the diffusivity version of the thermal conductivity are overlapping over a range of temperatures where both are changing. And that gives me confidence that this 30% fudge factor was a reasonable thing to do. So, okay, and then once you've got that, you've got the Lorentz ratio, and there's physics in there that I could elaborate on in detail, but it's not for this conference. So then we go into this overlap mode for better spatial resolution. And what you're seeing here is another ruthenate, calcium-3 ruthenium-207, which is rumored to have the possibility of being altermagnetic, but that's not what we were looking at here. This is just to show to you that in principle, you can map, it's an orthorhombic material with an anisotropic thermal diffusivity. And what we're doing here is just mapping the anisotropy of that thermal diffusivity as we go across a twin boundary. So just to demonstrate that the spatial resolution really exists. Okay. Now I'll show you the second example of what we've actually done so far, and this time with uniaxial pressure. So here we're going to be doing birefringence mapping across our domain boundary. But what we start with is something much more like the microscope that I showed you at the beginning, right? This is just polarized light microscopy on the sample it's in the pressure cell, but the pressure cell isn't in the laser setup yet. And this thing has structural twin boundaries, and so here's the domain structure at ambient pressure at room temperature. So what we then do is we bring that pressure cell away from the first microscope, we put it in the Montana cryostat. Control that you have to make a measurement like this. And again, we lock into the response at the chop frequency simply for signal to noise reasons. And what we're now doing, if you look to orientate what we're looking at from room temperature, here is the picture. This box is now where we've done the scans of the laser to measure the birefringence using the laser setup, both at room temperature. It means that we can use both different techniques to measure the size of that domain. And then I said we mostly cancel out differential thermal effects, but not completely. So as you cool down, if you're not correcting for it, you do put a little bit of uniaxial pressure onto the system. And that had the effect of shrinking, changing the domains, moving the domain walls and changing the balance between the domains as you cooled, which are fairly standard stuff, right? So what you can then do is do line scans. So you just do line scans across the domain boundary as shown, and that gives you some idea of the sharpness of the domain boundaries. I mean, it's not hugely sharp. This is just a demonstrator experiment. But what we can then do is, at each of these temperatures, we can apply, in this case, 0.08 GPa of uniaxial pressure. And what you see is that at room temperature, when we did that, we achieved about a 32% change in the linear dimension of the domain boundary. You can do it again at whatever that is. I can hardly read my own writing, but that's something like, or not my own writing would have to be read back here at 250 Kelvin. Again, we get about a 30% change. But if we apply the same uniaxial pressure down at 50 Kelvin, or 100 Kelvin, whatever our base temperature was there, we don't change the domain at all. So obviously, the domain pinning and the domain dynamics is temperature dependent, right? Which again is no surprise. And I'm not reading any physics into that for you at all. I'm just showing you that this is basically the kind of experiments that one could do. So for the future then, we can measure the AC elastocaloric effect. We can do spatial domain mapping. There's no reason we couldn't combine them. We haven't done that yet, but that could be done if necessary. The other thing about AC strain modulation is that it may not just be useful for the AC elastocaloric effect. It may well be useful for locking in, as something you could lock into with your optics as well. So there could be tricks you could play with optics as you do that little wiggle of the sample length. We haven't used fields at all, and we only have the capability of applying fields parallel to the sample surface in the rig that we have, but they are available, and it's a permanent magnet, so it's not controllable. We're open to appropriate collaborations. The caveat's going to come in a moment. And the main caveat is it's been quite an interesting project to observe. This, of course, isn't a turnkey instrument. It's far from a turnkey instrument. And it's one of these instruments that requires people to have skills from 3 different fields, optics, cryogenics, and uniaxial pressure. And it's, as one sees, not many people have those skills all combined, right? And so if somebody here feels they do, then please come and talk to me, because we're looking to repopulate the group as the personnel turn over. One of the things we could do, and that I'm very interested in potentially, would be to do spin Hall effect characterization using spatial Kerr rotation, very much in the way that the Oshalom group did in this famous paper on gallium arsenide back 15, 20 years ago. In principle, that's possible. But the final caveat is, if you do want to be our collaborator, be ready to be patient, because each experiment takes several months. We now already have an embarrassing queue of samples that people have given us saying it would be lovely to see domains in this, and they do not yet have pictures of their domains, and that would happen to you as well if you collaborated with us. Okay, there's my conclusions. I hope that this was useful to you in some way, and thanks for your attention.